office bearers of Institution of Engineers, India, scientists, representatives of DRDO and academia, fellow professionals, young engineers, and dear friends. It is a pleasure to be among a community whose profession has always been associated with converting questions into workable systems. The theme before us today is artificial intelligence and Internet of Things for an inclusive and empowered society. Rather than asking what AI and IoT can do, as an administrator, I think the more consequential question today is what are we becoming capable of doing with them? And what happens when that capability moves faster than our institutions, our skills, and our safeguards? The question has become particularly important in 2026. We are no longer discussing AI merely as a system that answers questions. We are moving towards systems that can reason through a problem, use tools, write and execute software, inspect their own output, interact with other systems, and increasingly act on our behalf. The question is the transition from generative AI to agentic AI. Considering the change in software development a few years ago, if we see an AI assistant could suggest a few lines of code. Today, systems such as OpenAI's Codex can work across large code bases, modify files, run tests, and prepare changes for human review. Codex is now used by more than 4 million people every week. Recent research by OpenAI and academic economists also found that number of active Codex users grew more than fivefold in the first half of this year. Anthropic's Cloud Opus 4.6 provides another indication of where this is going. It introduced a 1 million token context window in beta and is designed for long running, complex tasks, including large scale software engineering and autonomous workflows. Claude is no longer merely completing a sentence, it can retain and work through a very large body of technical information. Google is also taking same direction with Gemini. In May 2026, Google observes that Gemini application had crossed more than 900 million monthly users across more than 230 countries and more than 70 languages. It also introduced more agentic functions designed to perform tasks proactively rather than to simply respond to prompts. These numbers tell us something important. AI is moving from question answering interface towards an operational layer. This changes the nature of both opportunity and risk. If you take cybersecurity, for example, until recently, sophisticated cyber attacks involved skilled individuals to conduct investigation, identify vulnerabilities, exploit them, and establish persistence and move laterally across systems. Now, increasingly, AI systems can compress several of these stages into an automated workflow. Anthropic's Mythos is an example of defensive side of this development. Through Project Glasswing, Anthropic gave a restricted version of Mythos to small group of organizations to secure critical software. In the first phase alone, the number of participating organizations reported more than 10,000 high or critical severity vulnerabilities. There were reports that their rate of vulnerability discovery increased by more than 10 times. The more important story is what happens when the same capability is viewed from the other side. Anthropic did not initially release Mythos as an unrestricted public model precisely because its ability to discover vulnerabilities and develop exploits autonomously presented a very significant dual use risk. And the recent security evaluations have made that concern more concrete. Reports on testing by UK's AI Security Institute indicated that Mythos 5, under controlled and deliberately permissive conditions, went beyond simply identifying vulnerabilities. It attempted unauthorized offensive actions, including social engineering behavior and in some tests showed the ability to coordinate with other AI agents. This is a very significant change in cyber threat landscape. There is another dimension which concerns me as a public administrator. AI systems increasingly operate on user data which is generated by us, that is transactions, locations, photographs, health records, conversations, financial behavior, travel histories, public service interactions. IoT gives society eyes, ears, and sensors rooted to the physical world. AI gives these signals the capacity to be interpreted, correlated, and acted upon. The next generation of engineers, therefore, could build systems that do more than forecast tomorrow's weather. They could develop regional climate models that examine ocean temperatures, atmospheric circulation, satellite observations, and historical patterns to improve the predictions of events such as El Nino, extreme rainfall, or heat waves. A farmer could receive a field level irrigation recommendation based on soil sensors, weather forecasts, and a crop stage data. A person with visual impairment could receive contextual descriptions from an AI system through a wearable device. An elderly person living alone could have a home system detect an unusual fall or prolonged inactivity and alert a designated caregiver. This is what inclusion should mean in technical terms. Not merely giving everyone access to the same technology, but designing technology compensates for differences in ability, geography, language, and circumstances. India has particularly an interesting opportunity here. The India AI mission has approved an outlay of 10,500 crores and envisaged a national computer infrastructure of at least 10,000 graphic processing units, GPUs, along with indigenous foundational models, data sets, startup financing, future skills, and safe and trusted AI. By March 2026, government reported more than 38,000 GPUs has been onboarded to the Common Compute Facility and were being made available to Indian startups and academia at a very affordable rate. This is not merely about having a larger computer, it's about technological agency. If critical public systems depend entirely on models, cloud infrastructure, or architectures controlled elsewhere, then efficiency may increase while strategic autonomy decreases. That is why Indian companies such as Sarvam AI is worth watching. Sarvam has developed models specifically with Indian languages and Indian use cases in mind. In February this year, it introduced Indus, powered by its 105 billion parameter sovereign model, describing it as an effort to build not merely an application, but the model, data, and interface layers within India. In March, they also open sourced its 30 billion and 105 billion parameters large language models. The significance is not that the Indian model must outperform every global model. The significance is that India must have capability to build, evaluate, deploy, and govern its own models. That is a very different proposition. We have seen similar change in India's space sector. Skyroot Aerospace has emerged as India's first space tech unicorn, and its Vikram 1 program represents growing participation of Indian companies in orbital launch technology. Vikram 1 is designed for a small satellite deployment with a stated capacity of up to 350 kilograms to low Earth orbit. It is certain that space technology and AI will increasingly converge. Imagine a satellite constellation continuously analyzing agricultural stress, forest fires, coastal erosion, and urban expansion. Imagine an AI system correlating satellite imagery with ground sensors and issuing a district level alert before disaster becomes a crisis. The engineer of the future may therefore not belong neatly to one discipline. They may understand electronics communications, cloud computing, machine learning, and geospatial science and public policy simultaneously. And this brings me to the question that probably concerns every young engineer around: what happens to these jobs? We should neither dismiss this concern nor exaggerate it. The World Economic Forum's The Future of Jobs report estimate that structural changes could create 170 million jobs and displace 92 million by 2030, a net increase of 78 million. But enormous occupational disruption in between. It also estimates that nearly 40% of the skills required on the job are expected to change. The most recent Stanford AI index gives us even more immediate signal. It reports that employment among software developers aged between 20 to 25 has fallen nearly 20% from 2024, while one third of surveyed organizations expect AI to reduce their workforce in the coming year. At the same time, the measured productivity gains are substantial in structural tasks, that is, about 26% in software development, 15% in customer support, and 50% in marketing. This is why the anxiety about basic coding, data engineering, and even parts of cybersecurity is not imaginary. If an AI agent can generate SQL, construct a data pipeline, and write a routine API, clean a data set, create a dashboard, and test an application, then knowing only how to perform those individual tasks is no longer a sufficient professional advantage. The solution is not to abandon engineering, it is to move upward. An engineer who only writes code may compete with a machine that writes code. An engineer who understands why the system should exist, what data it can trust, what constraints apply, and it could fail, and what consequences follow from failure remains indispensable. That ultimately is where AI and IoT become interesting. It is when thousands of physical signals become useful decisions. When a sensor detects a fault before a machine stops, when a satellite identifies a crop failure before a farmer sees it, when an AI system helps a doctor notice a disease earlier, when a city anticipates flooding instead of merely responding to it, when an airport predicts a delay before passengers begin waiting at the gate, and when technology gives a person with a disability greater independence rather than merely offering another digital service. The great challenge before the engineering profession is therefore not to make machines more human. It is to make technology more useful to human beings without making human judgments obsolete. We should be ambitious about AI, but we should also be exacting about it. We should build models that are faster, smaller, multilingual, energy efficient, and more capable. We should build IoT systems that are secured by design. We should build Indian models that understand Indian languages, institutions, and realities. We should build autonomous systems that know the boundaries of their authority. And we should build a generation of engineers who can ask the most important question before deploying any technology. I congratulate the Institution of Engineers Kochi Center for bringing together engineers, researchers, students, industry, and public institutions around a subject that is no longer confined to laboratories. The future of AI will be written by computer scientists, certainly, but it will also be written by civil engineers, mechanical engineers, electronics engineers, doctors, administrators, pilots, teachers, entrepreneurs, policymakers, and most importantly, it will be written by the young engineers in front of me. I wish the 39th National Convention of Computer Engineers every success. Thank you very much.